So I'm Gyorgy Feher. Right now I'm in Paris at LBTH. And I would like to talk about integrable supersymmetric chains, an integrable supersymmetric chain conservation. This was a research which I partially did in Amsterdam and University of Melbourne. And so basically what we did, we introduced a new model, a new chain model. So first I'm going to define this model. I'm going to address the question of solving this model by beta ansatz. So this model, a bit surprisingly, turned out to be integrable, and we solved by beta ansatz. And after that, I'm going to talk about the symmetries of the model. So, as we discovered, this model has high degeneracy at every energy level. So, we wanted to find the reason for this high degeneracy. So, this is the main question I will talk about. And another thing is the completeness of these beta solutions, which was already addressed in the previous talk. And then I will conclude. So the original motivation or the history of this model starts with this paper by Fenley, Sultans, and De Boer, who defined an I equals 2 supersymmetric model. And so to define this model, you have to introduce lattice fermions, so they are spinless, and they satisfy the very usual anti-commutation relations. And here I and J are the lattice indices. And you can define a new operator, this D plus, which generates an isolated fermion. So given that these two sides, I minus 1 and I plus 1, are not occupied, it can generate a fermion in the middle. And this D operator, with the help of this D operator, you can define n equals 2 supersymmetric charges. So two operators, this Q plus and Q, which are nilpotent, and they are defined as such. So you sum up of this D operator over the length of the chain, and well, actually use periodic boundary conditions. So with the help of these Q and Q plus operators, you can define your Hamiltonian, which turns out to be, if you compute it, it turns out to be in this form. So this was their work, and the idea. Sorry. Yes, sorry. Okay, so P is the vacancy operator. So it at site I, and then this H, so this Hamiltonian, which is defined as such. If you compute it, it includes two terms. So there is this hopping term. So a fermion can hop from site I to I plus 1, or vice versa, given that the site I minus 1 and I plus 2 are empty, so because they are isolated fermions, so they cannot move closer than one side away from the other. And there is a kind of an on-site energy term, which is the diagonal term in this Hamiltonian. Sorry? Yes, this is not the model I'm going to talk about. This is the model of Fenley's score, and this was the starting point of our research. So the idea of our model was to make this model, which is shortly described here, make fermion all symmetric. So this is what we're going to do. So again, here is the canonical and anti-commutation relation for spinless lattice fermions. And let's now formally introduce this fermion number operator and fermion hole or vacancy operator on site I. And we define the standard Fock space on this lattice, so it's a very standard thing. And we define these D operators as previously. So this D, let's say this D plus, it generates a fermion at site I, given that site I minus 1 and site I plus 1 are empty. And the D, it makes it disappear given that these two sites are empty. And to make it fermion wall symmetric, we introduce other operator, which is the counterpart of this operator. We call it E. So this it generates a wall given that at site, so it generates a wall at site I, given that at site I minus 1 and at site I plus 1 there are no walls, so there are two fermions. And this EI plus is the reverse operator. So simply speaking, what these operators do, D plus and D, they are mapping between these two states, and EI and EI plus, they are mapping between these two states. So I hope this is clear, right? And after we did this, we can introduce new supercharges. So these are our supercharges, or Q and or Q, which are defined as such. So they are fermion wall symmetric extension of the previous supercharges. And these two supercharges turn out to be still nilpotent. So you can define a Hamiltonian as such with the help of them. So if you do all this, it's just straightforward computation. Yes. So E is how is it? So E is an annihilation. So the dagger and the non-dagger is always with respect to the fermion. Sorry? Yeah. So yeah. So if you make this computation, you can expand this Hamiltonian into three terms. So yes. So there are three terms: H1, H2, and H3. So H1 is the original term, which Hamiltonian of the original model. Now I wrote it in a bit different form, but it's actually the same. H2 is the same kind of expression as H1. The only thing that now all the fermion terms are exchanged with all terms. So it's the identical expression after exchanging D with E. And there is an H3, which is like a mixed term. I will explain the terms also in this. So yes. So in order to completely define the model, we can introduce either periodic or anti-periodic boundary conditions. Mostly we will work with periodic boundary conditions. I will give some comment on the anti-periodic boundary conditions, but mainly we work with periodic boundary conditions. So the main question: what are these terms which are in this H1, H2, and H3? Which are the processes which are described by these terms? So I group them into six groups, and let's go through it. So this A term, this one, is an energy term. So it counts the number of 0, 1, 0 and 0, 0, 0 strings. Yes. The C, it's the fermion wall symmetric counterpart of this A term. So it counts the number of, so it's still an on-site energy, and it counts the number of 101 or 111 terms. This term B, so this one, it describes the hopping of an isolated fermion, so it can hop to the left or to the right. And this D, not so surprisingly, it describes the hopping of an isolated and so because, okay, so this is a fermion model, so there are, because of the anti-accommodation relations, there are certain signs and a minus sign has to be introduced. Yes. And then these mixed terms, there are E and F. So E, it describes that if you have a string which is 1, 0, 0, 0, then two more fermions can be at these two sides. And F is a very similar term, just if you have a 0, 1, 1, 1 string, then two fermion can be eliminated. And also now this with a minus sign. So actually these mixed terms, which are responsible for the non-conserved nature of the fermions, so you can clearly see that you can generate and annihilate fermions. Right. So, since the fermion numbers are not conserved, they are not the best degrees of freedom to do beta ansatz. But if you look at, so you have, let's go back here a bit. So you have E and C, they are on-site energies, they are the diagonal terms, they are fine. And then you have these four kind of processes. So let's look into them. Now, I just erased the sign because that's not so important. So, if you look at these, you can introduce domain walls, which separate zeros from strings of ones. So let's do this. Here I have to introduce two domain walls. Here again I have to introduce two domain walls. Here I have to introduce one, and again one domain wall. And now you can see that these four processes can be described as hopping of domain walls. So the first two is there are two domain walls next to each other, and then one is jumping over the other one, or well, both moving away, whatever you want to think about. And the last two is a movement, a free movement of one domain wall by two sides. All processes in the language of these newly introduced domain walls can be, so that's such. And what do we see here? So we see they are conserved, obviously. Also, they are not only conserved, but their parity is conserved. If you have so I can introduce even and odd domain walls when even and odd refers to their position. So let's say if this is one, then the next one this is an odd one, and if here would be one that would be again an even one. So because they always jump by two sides, their parity is also conserved. So I can introduce two kind of particles, even and odd domain walls. And because they are all conserved, and there are two kind of particles, the whole Hilbert space can be divided into sectors, and I'm going to denote these sectors by mk, where m stands for the number of the number of domain walls, including odd and even, and k will stand for the number of odd domain walls. So this. That's a very good question, and not really the answer. Okay, the problem with domain walls, just very quickly, maybe I can talk about this at the end, that you have to always introduce two. So you can only create two domain walls at the same time with periodic boundary conditions. So we are talking about periodic boundary conditions, and then it's then it's somehow a very non-local operation, or that's the main problem. So somehow you can do something, but I didn't find it very useful yet, unfortunately. But I will address this at the very end. So, okay. So now I want to do beta ansatz. I want to do beta ansatz. It's in order to do so, I have to use a kind of renaming of fermion strings. So if you have a string, you can throw your domain walls, and then to this state I will attach. I will rename it that there's going to be x coordinates which are stand for the domain walls. So x1 x1 is 3. It means that the first domain wall is at position 3. Now the second domain wall is at position 5. The third domain wall is at position 8, 9. And then for every, and I will, this is a bit redundant information, these P's, I will just include here that which are the odd domain walls out of these domain walls. So I have 1, 2, 3, 4 domain walls, and out of these 4 there are 1, 2, 3 which are odd. So the first, second, and the fourth domain walls are odd. Okay, this is just it maybe sounds a bit complicated, but it's not. And then there is one more information to completely describe this state. Namely, I have to say that so every domain 1 can be either with a string of zeros and then continue with a 1, or the other way around. So I have to somehow distinguish this state from the other one when the zeros and 1 exchange. I just put here that the first state is occupied by a 0, so that's why I put epsilon equals 0. It's a bit technical, but I hope it's more or less followable. It's just necessary to do this in order to do the beta ansatz. Okay, so just one more motivation before doing the technical part. So if we did some numerical checks up to, I don't know, system size 10, and what we saw is like roughly characteristically this kind of spectrum. So these are the energy levels. You can this is for, I think, for L equals 8. But so these are the energies. You can see that they are symmetric, and also that the length of these energy levels is proportional to the degeneracy of that energy level. So, okay, on this picture, there is some kind of fairly big degeneracy, but also if you let's say plot the degeneracy as the function of the system size, you can see that it's proportional with 2 to the L. So it's an extensive degeneracy of the ground state, but also our expectation is that every energy level is some kind of exponential degeneracy. Just, I don't know, it's not so easy to define it for higher energy levels because there are more and more. Okay. And yeah, and so here is the completeness question. I will talk about that too. So let's do beta ansatz. Everybody knows that's here. I hope so. I will run through it, or I don't know. If it's really boring, let me know. It's a bit technical, sorry for that. So let's define our eigenstate set. So these are all the possible vectors in a given sector. So in a given sector with m domain walls and k odd domain walls. And these are the wave function amplitudes. So this is the eigenvector. So this is the equation we want to solve. And in order to do it, we will introduce this SI plus minus operators, which basically moves the ith domain wall. So this SI plus minus, it moves its value to 1 by left or 1 by right. And we have two kind of so this SI, they are not physical processes, so at least because they jump by 2 sides, at least SI square will need it, but we use that. And because there are two kind of particles, have a nested with So this is the warm-up to do two zero sector. That's the simplest case. So you have two domain walls, and both of them are even and know what domain was. So that's going to be very simple. So if there are two possibilities, these two domain walls are either far apart or they are two sides apart. If they are two sides apart, they cannot go closer. So this one cannot jump here, and this one cannot jump here. While they are far apart, they can jump in both direction. So these two cases are written here. So basically, you can see that here, if they are far apart, then this expression includes or moving of the domain walls. While if they are close by, then there are only two terms. And this L minus 4 terms is coming from the on-site analysis. I didn't pay that much attention to. Okay, so you do this, you multiply it with your eigenvector. So then you get the eigenvalues here, and you will get certain wave function amplitudes here. So here you get wave function amplitude and wave function amplitudes, but at different locations. So if you compute these, then basically you get these equations. So these curly sides, they are the wave function amplitudes. And okay, so there are some complicated equation describing the relation between psi I x1 x2 and involving x1 x2 plus 2 minus 2 and so on. Okay, so we take this second equation and make an analytical conjugation, and then we get such an equation, and then we just want to use the very simple coordinate beta on that. So this looks a bit complicated, but these complications are just coming from the science. You can detect the problem. The main thing is that you have the two amplitudes. Okay, you have an overall amplitude, but you have two amplitudes. And you have the two beta roots, Z1 and Z2. There is some I to the whatever phase vector, but it's not important. And then Z1, and then you have the two coordinates, and you have both permutations. So this is described here. And if you plug in this ansatz, then you get this concentration on the eigenvalue and on the amplitude. So they have to sum up to 0, and there is a certain this expression to the eigenvalue. And if you want to get the full solution, you have to utilize the periodic boundary condition. And from the periodic boundary, you get this condition on the wave function amplitudes, from where your very, very simple beta equations, since as you can see, this is just this is basically the free fermion beta equation. So this is very easy. If you do the same for an increased overall domain was, but still with 0, so know what the domain was, then you will get the same equations just for more particles. So this is very simple. Now, okay. And because of Pauli principle, the squares of these beta roots cannot be equal. Yes. So this is free fermionic. This is not so interesting. Let's make it more complicated. Let's look at 2 1 sector. So that's 2 domain walls, but out of this two domain walls, one is odd. So 2 different kind of particles. So here again, we write down two equations. So there are again 2 possibilities. Either they are far apart or they are distance apart. And depending on this condition, you have 2 different equations as such. And now you do the exact same thing as before. So, okay, I not even wrote it down. I was too lazy for that. But so you multiply it with the eigenvector, and then you get the wave function amplitudes, you get these two equations of the wave function amplitudes. They are just ugly. There is nothing so interesting about them. And these were equations where the first domain wall is at the odd position, but you can get similar equations when the second domain wall is at bottom. And then you will apply a two-level ansatz. So you will take this ansatz, which is, so you sum up for all information, and here you have the amplitudes. But this amplitude it includes further factors. Yes. And if you plug this in, then you get the same eigenvalue and the same condition on the amplitudes. And for this f g functions, you will get these solutions, where this u is the nested beta root. Okay. And again, to get the full solution, you have to utilize the periodic boundary condition, and they are such equations. And after all, you get these beta equations. So they are for the two one sectors, so particle and one odd particle. But from here, it's kind of easy to see how to generalize it. So basically, what you see that there is z1 to the L or z2 to the L is proper. So there is some overall phase vector. It's proportional to this term, where this term is exactly the f function. And on the nested level, you will have this beta equation. Yes, and here the product runs over the z's. We have still Pauli principle. It's okay. It's worth to mention that if you plug in u equals 0, then you will get back free fermionic solutions. And there are fermionic solutions also here. The eigenvalue has the same form, and now I just shortly go to the general ansatz when there are two n domain walls and m odd domain walls. So the general nested ansatz look like such. Yes, and you get these conditions. So you get the same expression for the eigenvalue. So the eigenvalue, so it runs over all the z's, so only on the first level beta roots, and the amplitudes are signs of the permutations. And this is the general form of the beta equations. Yes, so this is the first level, and here the product runs over all the u's, so all the nested beta roots. And the second, the product runs over all the z's. Okay. Yes, so the eigenvalue only depends on the first set of beta roots, and the Pauli principle utilized as such. This is the most general nested coordinate beta ansatz for this model. Okay, so we did this. Now let's ask questions. First question: if this produces all the eigenvalues, so if this solution. So and the other question is if we are able to explain the extensive degeneracy with the help of the beta ansatz. So let's talk about first the degeneracy. So the model has a lot of symmetries. I think you are already now know some of it because I was just constantly repeating it. So for the domain wars are conserved, and even no domain wars are conserved separately. And then there is a translation symmetry. So obviously, if you have a periodic and you shift the sign indices by 1, which is basically changing the roles of the odd and the even domain was. It doesn't change physically anything. So these two has to be mapped to each other, and they have to have the same properties. There is the supersymmetry, the Q and the Q-dagger operator, which act as such in a given sector. So it increases. Okay, let's see. Q is increased the number of domain walls by 2, and the number of domain walls by 1. There is a particle parity symmetry on the level of fermions. Yes. There is the fermion wall symmetry, so this is how I build up the model, so this is not so surprising. So we can introduce this gamma, which exchanges the role of all the walls and the fermions, and the Hamiltonian exchanges with this gamma. There is a non-developable symmetry. Maybe that's also very simple to see. So maybe I'll do it here. Is this visible here? Okay. So if you remember, for all the processes, and these are the domain walls which are jumping. But equally, I can just introduce non-domain walls. So whenever there are no domain wall, I introduce a non-domain wall, and then these processes can be described as jumpings of non-domain walls. The only thing, so this yellow curly line stands for the non-domain walls. So the only thing is that the role of these two, when there are two domain walls, are exchanged with the role of these two when there are one domain. So it's fairly easy to see that there is a domain wall. Oops, I hope I didn't destroy anything. So a domain one on domain wall symmetry is which is defined by this operator. Yes, and then there is also a shift symmetry, which I don't have a good intuition why it exists. It was just discovered and described by such an operator. Okay, so it's a lot of symmetry, a lot of degenerate can be explained by it, but none of these symmetry which increases by the system size. So this is basically not enough to explain the extensiveness of the degeneracy. So we need something more. Then yes. Sorry? Yes. Yes, so basically yes, there will be. Or I mean at the end I'm going to explain the extensive degeneracy. Or okay. Just so that by extensive degeneracy I mean that the degeneracy increases by, let's say the ground state increases by system size. So these properties them could explain. Yes, yeah. The ground state is degenerate and extensively. So the number of ground states it's proportional to the L. Well, L is the system size, and there is some proportionality factor here. Okay. So there is one more symmetry we discovered. It's technically it's not a symmetry. It's it's a reflection symmetry of the spectrum. So what we observe that spectrum is reflection symmetric. So if you take the spectrum, you turn it around, you get back the same. You get back the same spectrum. So for every state with a given energy, so let's suppose that the minimal energy is 0 and the maximal energy is L. This is actually the case for L equals 4n. And I think I forgot to say something. That, of course, I always considered even system size, because otherwise, with periodic boundary condition, the role of odd and even domains would have been mixed. But that's not the case. So I think I didn't emphasize it. Now, even make that more restrictive by looking at L equals 4n. And by looking at L equals 4n, we see that minimal energy is 0, the maximal energy is eigenenergy is L. And what we see that if there is a state with energy delta L, and there exists another state with energy L minus delta L. So the whole spectrum is symmetric, including degeneracies, yes? But they have the same amount of degeneracy. So this energy level and this energy level, it is. Yeah? Yes. So yeah. So the ground state and the highest energy state, there are equal number of, including those, everything. So I can, as on the picture. So if you just, here. So if you see that this is in pair with this, and then the length is the same, so it's equal number of states. And also for the intermediate states. So this is in pair with this is in pair with this. Oh, it's not the same, sorry, that's not the same, no. Yes? Yes. It just, I didn't talk about that because, it's, that's a bit more complicated. As we increase system size, there are more energy levels, and then sometimes the degeneracy of some of these energy levels decreases. So it's not just how to define successively increasing. But, so back to, here. Yes. Let's go back here. So we want to describe somehow this reflection symmetry of the spectrum, and to do so, we define this M operator, and this M operator. In a moment, I'm going to tell you what this M operator does intuitively. So, but it can M operator. It doesn't exchange with H, but if there is an eigenvalue, then after applying M, or first applying M, then you will get back this other state. So indeed this M operator describes this reflection. Now, to understand how this M operator works, let's look at a ground state and the highest energy state. So it's very easy to see that this state is a ground state. This is a ground state, because there is a domain wall at every second site, if you see. So out of those processes, none of them could occur. So there are only the on-site energy terms. And if you compute the on-site energy terms, you can see that the energy of this state is 0. So this is a ground state. And with kind of the same logic, it's very easy to see that the empty state, so the original vacuum of the Feher is the highest energy state because there is no domain wall, and with the same logic you can compute that the on-site energies at the end give value L. And so these two are in pair, and what this M does, it creates, so from this state, at every, so the first, second, and then the fifth and the sixth side, it creates fermions. And by doing so, it is this reflection. Okay, but it's still not extensive. So, what is the extensive degeneracy? Is this is explained in terms of so-called Cooper pairs. So, to do so, let's look at the beta equations, which look like such. Now, what we will do, we will two more odd domain walls with imaginary rapidity and with complex conjugate imaginary rapidity. So, if you have a solution as such, and then you introduce two more u's, then what is changing? So, on the first, in the first equations, there is a product running over the u's. So there are two more u, but since they are complex conjugate pairs, it's an elementary computation that their product just simply gives one. So there are two extra terms in these equations. However, they multiply to one. So these equations are still satisfied. Now here the product runs over the z's. So there are actually two extra equations, and which has to be satisfied. So in order to choose the value of these two u's, there are equations in these forms, where instead of this UL, you have this IU, or this U1. And Z's are already given because you took an already existing solution, so Z's are already given. And that's a consistency condition on what kind of new U's you can choose. So this is how, if you have one solution, by introducing two more, so keeping the number of all the domain was, so the particles, but increasing the number of odd domain was, you can introduce new solutions. I hope this is understandable, but I can maybe explain a bit more. Okay. And if you let's say it starts from a free fermionic solution, so when this first equation is basically this term here, it's Zj to the L is proportional to 1. Then typically you can solve this consistency condition which you get from here, and you can generate more solutions. Now, because the number of domain walls, or the maximum number of domain walls and odd domain walls depends on the system size, and this procedure works as long as you can still add new odd domain walls to your existing solution. It's kind of clear, or that this can explain actually exponential degeneracy. And then we did a more detailed analysis for the ground state, and we indeed saw that this explains exponential degeneracy. Okay, so there's one more I would like to address, namely if the beta solution gives the complete spectrum or not. And the answer is very simply not. So we just looked at some cases, and we saw that finding all the beta solutions, we didn't get the full solution. However, what we did, that now we applied some of these symmetries, which I just talked previously, and with the help of these symmetries, you could generate states, and then you could get the full symmetries. And we did this for a number of cases. I mean, yeah, what we find, so we find that probably this algorithm of generating all the solutions is something very complicated, or like the different cases we looked at, there were not any apparent similarities how the symmetry should be applied, and so it's just some for some cases. And then we looked at we could find the ground state and the first excited state. We could find explicitly the ground states and the first excited state energy. So this is the first excited state. This substrate is wrong. So we could find these two energies, and based on that, we can see that the gap disappears as 1 over L squared with the system size. So it's a sign of a diffusive behavior. And okay, I will conclude. So what we did is we defined a new supersymmetric fermionic chain with spinous fermions, and this had an extended system. And then we solved the model by coordinate nested beta ansatz. And then we had a lot of symmetries, including this zero mode Cooper pairs, which explains the extensiveness of the degeneracy. And then we find that the beta solutions with symmetries recovers the whole spectrum. And there are some open questions left. So we did coordinate beta ansatz. We don't have an R matrix. It would be nice to find the R matrix for this model and do adversarial ansatz. And this is where when this question arises that so ideally you would like to do beta ansatz in some conserved degrees of freedom. So you would like to do it in the domain was, but as I just told Ara, it's not. We haven't found any good way yet to define some creation operators for the domain was, because, as I said, they exist only in pairs. So I don't know. And then also, so we could explain this extensiveness of the degeneracy with the beta ansatz. I don't know what is the operator which would describe this. And maybe we can do